So let me give you a big picture here. What we are doing is applications of integration, and so this week we're going to be talking about solids of revolution, and at the end of the week we are going to have a much needed test. Now we have a half day Friday.
No, we don't.
No, they canceled.
Canceled it. We no longer. Okay, then let's do it Friday instead.
Why?
We have like 3 whole snow days this year.
So we'll be talking about solids of revolution for the next few days. If you have not yet seen the video on integrating with horizontal rectangles, shame upon you. Remedy that situation as quickly as possible. Yep.
So this is just like wrap up. I think we have some spring break this week, and that should be great.
Oh, wow.
No, spring break is going to spring break starts on the 28th.
This is next
Oh my
week
God.
after.
Seriously?
See how the calendar goes.
Sorry, never mind.
Spring break starts here, so 1, 2, and 3-ish.
And that's what we need to do in
Right, you can kind of like compare that to one answer, but not like 100%.
That's what it's getting. She's like, that's what told me, like, oh,
Okay, so let's start off with the stuff that you know. Go. The key thing that I'm going to be looking for here is correct representation. So there's a process that we walk through the house. Where does that process start? Where does that process start? No, where does that process start? Guys, where does he need to start? With a sketch. What line is it?
That's only one of these. Right, just do it. I want to, okay. That's what I thought. Gotcha. Gotcha.
Mr. Esau.
Yeah, that's true. Or just do 2 is 2. 2 to the 30 feet. 8 times 2. Yeah, you're right. 16 over 3. Okay, hold on. Go down. Yeah,
A lot of your sketches are missing the representative rectangle.
Yeah.
That representative rectangle is not an optional decorator, it's a thinking tool. Charlie, do you figure it out? Put it
How do you do this? And noticing. Yeah, it was.
See, the 3 has power means 2 to the 3rd power is square root of 4, square rooted to the 3rd power. No calculators, people.
No plastic.
No plastic. What the representative rectangle is showing.
If you don't get the exam, you may have to take it.
Like which that you're integrating vertically or
Yeah.
So your representative rectangle should show you what your top curve is and what your bottom curve is. Charlie, tell me what the top curve is.
Square root of x.
And what's the bottom curve?
Right.
Yes. Actually seeing it helps you to see it. So that we have the area is equal to, well, the area of my representative rectangle is equal to top curve minus bottom curve dx, so that the area is now going to be the integral from the first to the last of dA. And that's it. And so now we have 4 to the 3 halves minus 0, which is invisible. And now with regard to the exponent, we're going to think about this either as first the square root of 4 and then that cubed, or else 4 cubed and then the square root of that. One of those is easier. Which one? Square root first. So first the square root of 4, which gives me 2, and then 2 cubed, which gives me 8. And we get 16/3 as our area. And there it is. Describe some of the difficulties that you had. Some of you had difficulties as you went along. Bethany, one thing you learned from this. X equals 4 is a vertical line and not a point. That's exactly right. Charlie, one thing you learned. Representative rectangle is a necessary thinking tool. One thing you learned. You start with the sketch. Yep, exactly it. One thing you learned. I don't like fractional exponents. She would like to get to the point where she likes fractional exponents because who likes to be beaten up by things? Anybody? No. So, in terms of fractional exponents, how do we think about it? How about first this one, then that one? Right. So either the denominator first and the numerator, or vice versa.
I got confused on if like the exponent was 2/3 or 3/2. I did it the other way. Right.
Because you see the exponent here. So add 1 to the column. 1 half plus 1. I think it's 3 Okay. What we're going to do now is we're going to do something new and interesting geometrically. We're going to take this region, R, in blue here, and we're going to imagine it as a solid filled-in plane, like so, which it is. We're going to take that plane and we are going to revolve it about the x-axis. Picture that for a second. A couple of my robotics guys have been working with a program called Inventor, and Inventor does this automatically, right, the revolve thing. And so take this plane right here and revolve it about the x-axis. And when you do, if you take it all the way around the x-axis, what it forms is a shape that is called a solid of revolution. And this particular solid of revolution looks kind of like a bullet. Just like that. Can everybody visualize that? It's poorly drawn. One of my aspirations in life is to take some art classes at some point so I can draw these things better. But you can sort of picture it. There we go. And so you end up with a 3D shape that is a... Delilah's like, that's horrible.
Wait, that's what? It's horrible.
Can anybody draw this better than this? Maybe this would be great. Maybe I should do dotted lines for perspective.
Great adventure.
Yeah, no kidding. Is that any better? Yes. Okay. Okay. Cool. All right. So this is our solid that we get when it's revolved about the x-axis, and we call this a solid of revolution. And we might ask several questions about this. And one question that we might ask is, what is the volume of this solid? And a second question that's more complicated might be, what is the surface area of the solid? How much paint would it take to paint it? We'll address the second question, Calc 2. For now, we're going to ask this question, what is the volume of this solid? You could. For this one, you wouldn't want to. And so the way in which we're going to, our goal is to find the volume of the solid of revolution. And to do this, we're going to use a method that goes actually all the way back pre-calculus to a method of Archimedes. Archimedes is the famous bathtub guy, right? Eureka. I figured it out. And what Archimedes did, and then later Cavalieri, and then finally calculus people adapted this, was to take our solid of revolution. Let me draw it like so, in perspective. Here's our solid of revolution. We're going to take our solid of revolution, and we're going to cover it with a bunch of circular discs. That's horrible. Let me try drawing it like this. Here's a circular disc, and then I'll put it on its side. Okay. So that our circular discs are now going to cover, like so, and approximate the volume of our solid of revolution. There. That's the very best that I can do with that. Even if you can't see the artwork, can you understand the concept?
No.
Yeah. Take our solid of revolution here, and take a mathematical knife and slice it. Just like you would slice up a sausage or a salami or something. Okay? And now you have these really thin slices that are approximately circular discs. Okay? So our basic method is to slice the solid and when we slice the solid, here is our key phrase. We're going to slice it perpendicular to the axis of revolution. So let me talk about that for a second. Our curve lives on the xy plane, right? And our axis of revolution, in this case, is the x-axis. We are revolving about the x-axis. So that when I slice my solid, I'm going to slice it perpendicular to that axis. I do not want to slice it parallel to the axis of revolution, because if I do, I'll get shapes that are not circular discs. They're going to be some other weird shape. And I sure as heck don't want to slice it like along the line y equals x or anything like that. So when I slice it perpendicular to the axis of revolution, what I get are resulting shapes that are approximately circular discs. Please notice that discs is spelled with a C as opposed to computer discs that are spelled with a K. The resulting shapes are approximately circular discs. And the reason that I care about that is this. I can easily find the volume of a circular disc. And if I now add up the volumes of those circular discs, I get an approximation for the volume of the solid. And if I let the width of those circular discs now go to 0, then my approximation will become exact. So let's see how that process would work. here I've got my solid of revolution, and I've covered it with 1, 2, 3, 4 circular disks. So I can say that the volume is approximately equal to the sum from I equals 1 to 4. And now I need the volume of my circular disk. Let's see here. Let's examine that question a little bit. If this is a circular disk right here, like so, then it's going to have a width, and the width of my circular disk is going to be the change in x along that x-axis right there. And the radius of my circular disk, well, let's call it r for now. And the r is going to be a function of x, because as my x changes from 0 out to 4 here, you can see that the radii of my disks are changing right along with them. So r is a function of x, and I'll call it r of x to indicate that. So we ask, what is the volume of a circular disk? Well, because the circular disk is a constant radius all the way through, therefore its volume is simply area times height, right? And so the volume of one circular disk, which we will call delta V, is equal to the area of the circle times the width of that disk. We're multiplying the area through the width. And when I now add up all of the delta V's, what I get is an approximation for the volume, just like that. The sum of pi r squared times width for each one of those disks. Well, the only thing I don't like about this is that my disks have a little bit of error in them because of that overlap. Does everybody see how this portion right here sticks out over my solid, and the result is that I've got too much volume? And so the way to reduce that amount of error is to increase the number of disks. And in the limiting case, as n goes to infinity, the amount of error is going to go to 0. And as a result, I get a legitimate Riemann sum, but it is not an area sum. Previously, our Riemann sums were f of ci times delta xi. Here, I'm adding up, instead of height, I'm adding up pi r squared. And so what I'm adding up, and what I'm integrating, is not f of x, or f of x minus g of x, but instead it is going to be pi r squared. So that this entire expression is the integral from a to b of pi times r squared dx, just like that. And because we generated this formula by slicing our solid of revolution into disks, we call this the disks formula. Or sometimes you'll hear it called the disks method of finding volume. The way that Archimedes did it was very cool. He did exactly what we did here. He used circular disks to approximate. He used basically a left sum and a right sum. So the left sum was too big, the right sum was too little, and he said that the volume had to be somewhere between there. And then he would let the number of disks increase, and as he did so, then the volume was squeezed between the left sum and the right sum. And he called this the method of exhaustion. Sounds kind of So here's our theory. How does this work out in practice? Here's how this is going to work out in practice. Let me remind you of our problem. Let R be the region defined by y equals the square root of x, x equals 4, and the y-axis. And our goal was to find the volume of the solid generated when R is revolved about the x-axis. Okay, so I'm just restating the problem right here. And here's how we would break it down. We'd start with a sketch. Here's my region R. And we understand that our region R is going to be revolved about the x-axis here. If it helps you to visualize it, I often will visualize it by taking this guy and drawing him down here. And I'm going to draw for myself a representative rectangle that represents the radius. It represents the radius of one disk that's going to sweep around and form a single disk here. This is a representative rectangle that represents one radius of the disk here. And I'm going to label that, just as I did before, dx. And I'm going to identify the value of that radius. That radius is going to be the distance from the curve to the axis of revolution. And the curve is y equals the square root of x, and the axis is y equals 0. And therefore, the distance between them is simply subtraction, root x minus 0. And I can identify that the radius is equal to the square root of x. Now, just as I did with area representative rectangles, so also here I'm going to spot check at the extremes. So according to my formula, when x is equal to 0, my radius should be 0. And that's in fact exactly correct. If I go to here and I say how much of a radius do I get when I revolve this point about the axis, there's no radius at all. And if I go out to here to x equals 4, at the point 4, comma 2, if I spot check my formula predicts that the radius at 4 should be equal to 2, and that's exactly correct. A rectangle right here would have a radius of 2 going around the axis. Everybody with me on the spot check? Okay? So I have the right expression for the radius. And now I can say that the volume of my solid of revolution is pi times the integral of r squared dx. And I'm going to add up those disks from the very first disk at x equals 0 out to the very last disk at x equals 4. And since r is equal to the square root of x for all x's, I have an expression for it, and I can plug in. And it's very convenient, because the square root of x squared is just x. Which gives me 8 pi as my final one. How are we doing? what I'd like to do now is I'd like to do a shape that we already know the volume for. So let's consider RV, the region defined by y equals root 25 minus x squared, and the x-axis. And our goal now is to find the solid, find the volume of the solid generated. When R is revolved about the x-axis. Hint, what's the name of the shape of R? Circle, yeah, exactly. Actually, it's only going to be half of the circle, right? The top half? Ah, yes, and when we revolve that half circle about the x-axis, what special shape do we get? We get a whole sphere. It goes all the way around the x-axis. A whole sphere. And we know or should know the volume of a sphere already, and so we can check that we're doing it right with this particular problem. Okay? So our sketch should look like this. And of course, Dohan, I'm going to start with a sketch, right? And there it is. And then I'm going to draw for myself a representative rectangle that represents one of the many radii that I'm going to get when I slice my solid of revolution perpendicular to the axis of revolution. So just imagine our sphere that we get when we revolve this about the x-axis. Everybody picturing that? Now I take that sphere and I'm going to cut it just like that. And this is key. I want the representative rectangle to be the radius and not the diameter. So sometimes people will try to carry that all the way through, and then they get 4 times the answer they should, because the diameter is twice the radius. And when you square that, you get 4 times the volume. Okay, so we have that. Now we're going to identify the radius here, and the radius is going to be curve minus axis. Notice it's not top curve minus bottom curve, but it is the distance from the curve to the axis of revolution, because that's what a radius is. And the curve minus the axis is going to be 25 minus x squared minus y equals 0. So that the element of volume that we're looking at that is defined by this, just this radius right here, is going to be pi r squared times its thickness, which is dx. And happy day, when I square the square root of 25 minus x squared, I just get 25 minus x squared. So that the volume is now going to be the sum of. Now, what are my limits of integration? What is the furthest to the left that I start integrating at -5? That's exactly right. And all the way to the furthest to the right, +5. Just like so. And this is totally, totally doable. I find that it helps students to remember the form. So if you would like to write it like this, that's probably a good idea, just so that you remember the form. Now, do you see what I see? I see that we could do half as much work if I integrated from 0 to 5 and multiply by 2, because the whole thing is symmetric, right? So I'm going to rewrite this as 2 pi times the integral from 0 to 5 of 25 minus x squared. And that gives me 25x minus x cubed over 3. And all of that from 0 to 5. Let's see, 25 times 5 is 125 minus 125 over 3, which is going to be 325 minus 375 minus 125, or 250. Yep. Just like so. Now, at the very, very beginning, I said that we could do this particular one more easily simply by a geometric formula if only we knew the formula for the volume of a sphere. Who's got that? Huh. What you got?
1/3 pi r cubed.
That's it, 4/3 pi r cubed. So we can check ourselves. Is equal to 4/3 times pi times 125, and 4 times 125 is 500. So the geometry and the calculus agree with each other. And by the way, Archimedes is the one who developed the 4/3 pi r cubed formula, and he did so by the method of disk sweeping function. Okay, so let's see how things, let's see how some variations can happen here with these. So let's let R be the region that is defined by y equals x squared and y equals 4. And we'll start with the area of R. Go. Hopefully your sketch looks just like this. Hopefully also you have a representative rectangle that looks like this, with the width of dx, and a height now of top curve minus bottom curve, 4 minus x squared times the width. So that the area is going to be the integral from the first x to the last x of 4 minus x squared dx. And here again we have symmetry, so it makes sense for me to integrate from 0 to 2 and double it. So that I get 32/3 as my final volume. Yes, ma'am?
In your equation of x times gx, how do you know which one's fx?
Top minus bottom. Yep. You want a pot, if you did bottom minus top by mistake, then you would end up with a negative value. And you want a positive height.
And in the first example, you have pi r squared dx. Why didn't you put pi?
Okay. So notice the difference in the question here. What we have here is the area of this region, just a flat area. How much area do we have? Now we're about to revolve it about something, and we'll find the volume of that solid revolution. So the second question, those are good questions. Did everybody catch that? Now we ask this question. Find the volume of the solid generated when R is revolved about the line y equals 4. So here is the variation that we're doing. Our axis of revolution is now no longer the x-axis, but instead is the line y equals 4. So that when I take this region and I bring it around the line y equals 4, I end up with a shape that looks somewhat like an M&M. Can you all visualize that? Here comes my region, comes up and over, around, like so, and I get a circular region, like that, whose cross-sections are discs, and the whole thing looks basically M&M kind of shape. Okay? And so I begin with my discs formula here. I begin by identifying, mentally I slice up my M&M into circular discs, perpendicular to the axis of revolution, so that I can draw for myself a radius. Look at that. My representative radius is the same representative rectangle I had for the area.
I was thinking it was an egg. It's more of an egg. Egg.
Not really.
Yeah, it's more of a soft egg.
It's,
Well, it's definitely not an egg.
it's more of an M&M shape than it is an egg shape, right?
Really?
Well, I guess like a oval, but like all.
I was really thinking it was really
Okay, yeah, okay.
It's more like a soft.
So I need to identify the radius here, and the radius is the distance from the curve to the axis. Notice here that the axis is on top. So instead of doing curve minus axis, I'm going to do axis minus curve. If you accidentally screw that up, it doesn't matter, because I'm going to square the whole thing in just a minute anyway. So if you accidentally do them backwards, you still end up with the same expression in the end. So that the radius is the axis minus the curve here. And my limits of integration are going to be from the first x to the last x. From -2 to +2. So now I end up with this fellow right here, and I've got to integrate it. My first thought is maybe I can substitute, but then if I let u equal 4 minus x squared, then du is -2x dx, and I don't have du sitting right there. So instead, I think to myself, maybe algebra, and that's in fact exactly what I need to do. That's going to give me 16 minus 8x squared plus x to the 4th dx. And again, it makes sense for me to integrate from 0 to 2 and double. Let's see, 64 thirds plus 32 fifths. I could be a hero of arithmetic, but it makes sense to me to just leave that. That's a perfectly good number. Okay, questions? We're going to pick this up again tomorrow, and we'll consider some other variations that can happen with regard to this whole thing.
Just go over a little bit.
Sure will. On your way out, guys, if I can have your attention for a second, please. On your way out, there's a lot of homework in the bin. Many of you on your integrations didn't actually show any checking, and some of you got problems wrong as a result of not checking. So I put a note on there, show your checks.